Hello, everybody. I want to explain something about the structure and evolution of the stars. This is one of my course for PhD, which its teacher is Dr. Ernst Ponce. He is my supervisor, and I want to explain you whatever I learned from this semester. And now from the first lecture, I can share my screen and tell you, explain you whatever I learned. Yeah, these are the fundamental physical constant which we should know, for example, radiation, density constant, velocity of light, and gravitational constant, other parameters that you see that we should know about them, and we need these physical constants for this course. Now you will see that the star life cycle. Here it's a nebula that stars, protostars actually were born, and if they are somehow like sun-like stars that we have, something like this, then when they become old age, they become red giants, and then for their death cycle, they become a planetary nebula, and then white dwarf and black dwarf. And stars are like human. They were born, and then they somehow they become young, and then they become somehow old, and then they will die, and there is a remnants of them after their death. For example, the future of our sun, like this red giant planetary nebula, that push its shell out, and it becomes like a white dwarf, as you see, and then it becomes like a black dwarf that we won't see it anymore, and we call it dead star body somehow. And then if the stars are 1.5 or to 5, or they are more than 5 times mass of the sun, that we call them larger stars or giant stars, they will become a red supergiant. Let me see. You see that they are so large. They have their radius is too large, and then when they become old, and then they will die. They die with a very very massive, and they explode. When they want to die, they explode, and we call it supernova. And then for the remnant, they have a Gaia nebula, like here, something like this. It can be also born some stars there, and then they become, for example, from their mass, if we see some neutron star or some black holes, they are the remnants of these cycles, as you see. And for star clusters, we can say that all stars in star clusters are at the same day were born at the same distance, at the same age, and dynamically bound, and also the same chemical composition. But the difference is in mass that I will tell you about it later. And they can contain 10 to power 3 to 6 stars. We want to explain it in this course, whatever I learned. For sun, which is the best study case for us, case study of us is sun, because it is so near to us and we can explore about it much more. Stellar interiors not directly observable. As you see, we cannot directly go to sun and have some part of that and then go that probe out and detect and explore or examine something directly from the sun, although it is the nearest star for us. But we can detect the neutrinos from the sun that they emitted from the core of the sun to us. And we have something that we call it helioseismology. Variations of solar surface can be used to probe density structure, must construct models of stellar interiors. Predictions of these models are tested by comparison with observed properties of individual stars. Observable properties of stars. We have some parameters that we call them. They are characteristic of the stars. When they are mass, as you see, M, luminosity, L, radius, R, effective temperature, T effective. And you see that these 4 parameters are dependent to each other. They are not independent. And for this formula, there are 3 independent quantities. And we have also other parameters too, like, for example, age, reddening, rotation, metallicity, that we talk about them later. And you see from here that we can measure flux, which depends on distance of the star and also metallicity. Here D is in parsec, and we can also, if we know about the distance of the star, we can know something about the luminosity and then flux. And we can determine the distance D if we measure parallaxes. You know, parallaxes, for example, we have a star, we have Earth here, it is sun, we have Earth 6 months later in this region. We can observe the neighbor star from here, and for the system Earth, Sun, B is 1. And from parallaxes, we can determine the distance. If we put the sun in 10 parsec farther, we can see that we have sun with the radius of 0.001 or 10 to power minus 3 arc-second. And we can compare it with Hubble resolution. With Hubble resolution that we have it in 0.05 arc-second. very difficult to measure or directly. It is really hard. And also radio stars measured with techniques such as interferometer and eclipsing binaries. How we can determine it with eclipsing binaries? For example, we have two stars. One of them rotate, although both of them rotate. If one of them goes behind the other, and then we can measure the radius of the star which is nearer to us. Here you can see the size of the Betelgeuse. And the other is the size of the Earth orbit is like this. Jupiter is this, and this is the size of the Betelgeuse. You see that it is too large. And we can say that we have most of the stars somehow the same radius as our sun, also in the main sequence. Because here we have sun, which is one radius. If we, as I told you, we measure sun as our case study, and it is the base of us. And we measure the other stars with sun. And we have not much stars that are that they are much more larger in radius than our sun. In Hertzsprung diagram, also we can say that luminosity is dependent on the effective, and luminosity also depends on mass. As I told you already, that they are not independent; they are dependent to each other: mass, radius, luminosity, and T-effective. 4 characteristics that I told you that we should know about the stars. And measure accurate T-effective or temperature, effective temperature for stars. For stars is an intensive task. A spectra needed and model atmosphere. It is somehow, we can say that it is hard to measure the accurate effective temperature, that we should know something about the model, we should have something, model atmospheres and spectra. And the magnitudes of stars are measured at different wavelengths. You see here, we have Vega because it is a young star and it is blue in color. We measured in ultraviolet spectra filter, and we have sun, invisible, and J is for infrared, and we have an old star, which is hot star, in infrared. We have something that we call it absorption or extinction or reddening. This is something that, for example, we have, we mostly call it reddening. We have reddening because we have, for example, consider that we are here, for example, in Earth, and we have a star or a star cluster which is far away from us, and between us and between, for example, Earth or our sun and that star, we have dust, gas, or something that we call it interstellar medium. And because of that, we cannot see that star perfectly. It is between observer and object. And differential extinction within one star cluster because of local environment. We have also in our Earth, we have, we have atmosphere, and atmosphere is somehow like a boundary or somehow like a barrier for us that we cannot observe the star cluster clearly. And because of that, we launched Hubble Space Telescope into space that we remove the Earth atmosphere in this case. So we can observe star clusters, other galaxies, and other objects more clear. And there are reasons for the interstellar extinction. Light scatters at the interstellar dust, and then light absorbed by heating of the interstellar medium. It depends on the composition and the density of the interstellar medium, that how it will be hot and can absorb the light from the interstellar dust. You see here that we can say we have more dust and gas in ultraviolet than the infrared. And or we can say the size of the dust is near the size of in ultraviolet. We have something that we call it absolute magnitude and bolometric magnitude. In absolute magnitude, if we put the, for example, star cluster 10 parsec away from us, we can define it as apparent magnitude. And in this formula, in this M with a small letter, it is apparent magnitude. This M with the capital letter, it is absolute magnitude. So apparent magnitude, absolute magnitude, and this is distance is in parsec, and then we can calculate the absolute magnitude. And we have a bolometric magnitude, which I can show you. For example, you see that we have some flux in ultraviolet, some in visible, and some in infrared filter. We have a bolometric that it's correct and have a measure of 3 of these. We call it bolometric magnitude. So we have just one plot of these 3 filters or flux. And we have minus in this formula. Why? Because we ship those 3 diagrams down to have just one diagram. So we have minus here. And for bolometric magnitude, we should have model, and it is not much easy. So most people do not measure the bolometric magnitude. Also, we call it bolometric correction. Here you see bolometric correction and absolute magnitude. And if we have a bolometric correction and bolometric magnitude, and for bolometric magnitude of sun, and we have luminosity and luminosity of the sun. That's it. In here, this is a Hertzsprung diagram for Gaia. You see, if we have some stars that the velocity of them is less than 40 km/second, we can say they are somehow young stars, and these are white dwarf. And also in here, they are somehow older, and also we have white dwarf but less. And these are stars that are old, completely old, and the velocity of them is more than 200 km/second. And the thing is, they are 3 different diagrams, but when they measure the color and absolute magnitude, they saw that the whole diagram, the whole 3 diagram of young and middle and old stars are in the same place. And we have no star here, also here and here. It is somehow fantastic that they are like each other completely in the same region. And the stars in here are not the stars in here and here. They are different stars. These are old stars and these are young stars. But the place of them, the location of them for all 3 diagrams are in the same place. And as I told you, luminosity is dependent on mass. And this alpha is 2 to 5, slope less steep for low and high mass stars. This implies that the main sequence on a Hertzsprung diagram is a function of mass. And from here, for example, if we consider it as a main sequence, we can say that from bottom to top, the mass increase. So, for example, in the bottom of the, if I can find some, yes. In the bottom of the main sequence, we have some stars that the mass is less than the stars in here. They are more mass stars. Here there are some less mass stars. So from bottom to top, the mass increase. Also, then the luminosity is increased in main sequence. Yes, as I told you. And then here we can say that we measure the mass and luminosity as here, but in logarithmic form, because it is somehow simpler for us to measure in logarithmic. And something about metallicity. X is for hydrogen, Y is for helium, and Z is for the rest, for example, iron or the rest of the metallic composition. But the point is the sum of the whole should be 100. 1 minus X minus Y is give us Z. So the sum of the whole should be 100 or 1. We have some problem about abundance with sun, that for hydrogen and helium, we cannot detect them straightforward in a spectra. Also, elements with only a few lines and only weak lines, we have some problem with them too. We can measure the age of the sun with meteorites and comets. Because they are old, they are older than our planets and many other objects. So we can measure the age of the sun with meteorites and comets. And you see, for hydrogen, helium, they are less. For meteorites, they are less than the sun, photosphere in sun, because they missed the hydrogen, helium during the time, during a long time. But for other elements, and also they have more lithium, and that the hydrogen, helium, and then lithium, they change the hydrogen into lithium. And you see, for other elements, they are somehow the same. They are like each other somehow. Also, you see, for example, here in iron, they are somehow like each other, but for sun it is more. And the thing is, maybe you think that we have iron, much more iron in sun than other elements, but it's not true. Against of this, we have hydrogen, helium, more than iron in sun. We have hydrogen, helium, other some light elements like oxygen, carbon, and nitrogen, and then we have iron in sun. And for isochrone, we can say that isochrone is dependent on age and metallicity, as you see here. And this is a Hertzsprung diagram for open clusters. We have, as you see, M67 is the oldest. And then, as I told you, if we go from bottom to top, we have more mass and we have younger clusters, and luminosity is more. NGC 236462 is the youngest in this main sequence, and these are turn-off point of some clusters. So for summary, we can say that in clusters, age and metallicity must be the same for all stars. But the difference is in mass. Stellar evolution assumes that the differences in cluster stars are due only or mainly to initial masses, that they was born in nebula, that how the stars was born with which mass. That mass is important. That mass, we call it initial mass. Cluster, Hertzsprung-Russell or color magnitude diagrams are quite similar. Age determines overall appearance. And you know that we have some difference with globular clusters and open clusters. In globular clusters, main sequence turn-off points in similar position. Giant branch joining a main sequence. But in open clusters, main sequence turn-off points varies massively. Faintest is consistent with globulars. In globular clusters, horizontal branch from giant branch to above the main sequence turn-off points. But in open clusters, maximum luminosity of stars can get to absolute magnitude is approximately -10 magnitude. In globular clusters, A horizontal branch often populated only with variable RR Lyrae stars, but in open clusters, very massive stars found in these open clusters. The differences are interpreted due to age. Open clusters lie in the disk of the Milky Way and have large range of ages. The globulars are the oldest objects known, tracing the earliest stage of the formation of Milky Way. They are somehow like in the same age of our Milky Way because they are too old. We call it the age of them somehow approximately 12 cross 10 to the power 9 years. But globular clusters are, open clusters are much more younger, and they are in galactic disk. Thank you for your attention. I hope I could explain you much more, and see you next time. Bye.